ST Robotics designs and manufactures small to medium-sized robots for precision applications. In most cases, they are required to perform linear movements in three-dimensional space. Internally, they're constructed around stepping motors which execute strict angular movements. Company CEO David Sands explains how one form of motion is converted into the other.
So the problem with robots is that in order to program it, the robot doesn't really work the way that we like to think. For example, if I want to pick up this bolt, I can start to move down, but as you can see, the following on joints are not where we want them to be. So then we try and straighten that up a little bit, but that isn't right, so I move a bit more down here, and so on. Human beings prefer to think in terms of left, right, in and out, and up and down. In other words, X, Y, and Z. So using Cartesian coordinates was much easier to control the robot and to have it go where we expect it to go. So here I'm trying to pick up this bolt. I'm nearly down where I want to be, and now I'm ready to grip. And then to pick it up, I can just move upwards. So our problem is that we want to position the robot in the way that human beings think, that is up, down, left, right, in other words, Cartesian coordinates X, Y, and Z. But the robot thinks in angles, and it's much too difficult to program the robot in angles, so we want to tell it where we want in real space, in real coordinates. Positioning this end effector to the X, Y, and Z positions that we want, I had to do some trig involving basically just breaking the robot up into triangles. Looking from the top, we have X and Y, and this will tell us what angle the waist needs to rotate to, and that's here. It also tells us what radius we need to reach. If we imagine this being on a circle, we now know what the radius is as well as the angle, and that's looking at it from the top. Looking at it from the side, in elevation, we have the radius that we calculated here, and we have our Z height, which could have been negative, but we'll think positive, and that gives us a length which is from the center of the robot to the gripper. So the center of the robot is here, and the gripper is here. This is the distance. So if you imagine this being my arm, we have the length from here to here. But the problem is, I don't want to keep my arm straight. I need to bend the arm so that that length is as I computed. So I need to know now what this angle is. And to do that, the arm will be in this position. And we need to figure out what that angle there is there. So we call this angle theta. Theta comes out from the usual equation where we have L, A and B. L squared equals A squared plus B squared minus 2AB cos theta. We want to know what theta is, so theta equals the arc cos of A squared plus B squared minus L squared all over 2AB, and that gives us theta. The angle of the elbow is of course just 180 minus theta, and that tells us how far we need to bend the elbow from otherwise being straight. So there is a primary processor which does these calculations, and once it's calculated what the angles will be, there's an angle here for the elbow, there's an angle here for the shoulder, and of course there's an angle here for the waist. Once it's calculated what all those angles are, it converts them into motor steps or motor increments, which it then sends across to a second processor called a DSP, a digital signal processor, which then actually drives the motors to the correct positions, and the whole robot then assumes this position that we've calculated.